morning everybody. Today we will be starting on another chapter which is D and F block elements. So, what are these elements particularly we should know, and what are those positions, and another name of these block elements are transition elements. So, one important definition for this is transition. So, these are transition elements, and if we consider their position in the periodic table, they run from group 3 to group 11 in the D block. So, we all know that when we start from left hand side of the periodic table, we find that group 1 and group 2 elements are there, and at some point of time we find that group 3 and up to group 11 will come, and these transition elements, and if they are present from the occupancy in the D cell, then we consider them as elements of D block. So, we will just go up to group 11. So, what about group 12? So, if we ask somebody that what are the group 12 elements, give some example of these group 12 elements, we know immediately some can say that we have zinc, cadmium and mercury. So, that question immediately comes to us that whether we should include group 12 within these or not, that we will discuss later on. So, what about these, that the definition of transition? What is the transition? Because of their position. So, in the periodic table they present in between S block and the P block elements. So, their position in the periodic table is important. In the periodic table, and it is between, here we have the S block elements and on the right hand side we have the P block elements. So, positioning of these elements therefore are important, and this position is the transition position from S to P. So, if these are S and these are P elements or P block elements, so we basically move or go for a transition from S to P via these elements. So, that is why these are known as transition elements, and in terms of their properties we will find that the properties are also transitional. These properties are also transitional from S to P. So, what is the transitional property? That means these properties will be in between S block elements and the P block elements. So, they are, first thing what we consider is their metallic properties. So, what are the metallic properties of S and P block elements like sodium, potassium, magnesium and calcium? We know that they are corresponding metallic in nature. So, when we move from them to these elements, we will find that they are also highly reactive. Metallic elements. So, if we move from these, so which is also very much similar to that of your S block elements. So, they also form like S block elements. As we slightly move from S to these, they will also form typically ionic compounds. and we know that the elements on the right hand side, including the halogens, they form the corresponding elements in the p block, but these p block elements are largely covalent. So, they will get some property inherited from these p block elements also, and in some cases in the latter part of the periodic table on the right hand side of these d block elements, they will also form some covalent characters, something related to these p block elements. So, as we know, so S block property is also there. So, some amount of p block property like elements of p block, as it gives typically or largely covalent compounds. So, some of these transition elements also will be responsible for giving typically all of these covalent character to this particular series. So, what we will find now that many of these properties, so these two properties we mostly consider, which are the physical properties. So, how we can consider, that means physical properties of these elements and the chemical properties, since we are considering their properties in relation to S block and P block elements. And what we are doing? We are doing in these blocks that we are adding electrons not on the ultimate or the outermost cell, but is the penultimate cell is responsible. So, we have the penultimate cell, and the cell is also expanded when we know that S is filled and P is filled, we get 8 electrons, but in this case the D level is filled, D cell is filled. So, we move from 8 to 18 electron occupancy. As a result, many of these physical and chemical properties of these metals, when you consider these as the metals, so they have the metallic property. So, metals of this group such as nickel, such as copper. So, what are these metals? So, they will have some properties which are in common, and they give rise to something which is typically the metallic property, that means they are good conductors. Such as for both these two things, that means they are good conductors for electricity and heat. Then they can have metallic luster, they are also hard and strong, because when we talk in terms of the metallurgical behavior of some of these metals such as iron, iron also comes into this category as the transition element of the D block element. How we can improve that the property which is strong related to the metallic property, and in some cases they are also ductile. And another property which is very much related to their physical property is that they also form alloys, alloys with other metals. So, this group of elements, how we can therefore define? So, we just go for now the definition, because the definition will consider all the species which will be there, and we will have, if we have the d electron configuration. So, the d electron configuration, whether the d electron configuration can have connection with this definition of these transition elements. So, that we will see from here that this not only the D, but also we will be considering the F block elements in a similar fashion. In the latter part of this chapter, we we will first find what are those F block elements. So, before that we will just consider what are these D elements and what are the transition metal ions. So, by definition a transition metal is an element whose atom has partially filled D subcell. So, the occupancy of these D subcell is important and which can give rise to cations with an incomplete D subcell. So, if it can give rise to some cations which have incompletely filled D subcell, then that particular metal or that particular element we consider as the D block element. So, you have the incompletely filled D orbitals. So, if we have the D cell or the D orbitals, then what we will find that these are all incompletely filled. And where these incompletely filled D orbitals or D cell in its ground state or in any one of its oxidation states. Which is therefore important, that the ground state configuration should give us an incompletely filled D cell or any of its oxidation states. So, when we will consider their possibility of the oxidation states, whether it has a one permanent or one very easily accessible oxidation state, or it can have the different oxidation state, whatever oxidation state you can have, whether you have a incompletely filled D cell or not, that will typically define whether you are talking about the corresponding element which is a transition element, such that the most common practice we know from early days of our schooling, that iron is there. We know that iron can have 2 plus or iron can have 3 plus. So, one we consider as a common name as the ferrous ion, another is known as the ferric ion. So, any of its ground states, basically that means whether it is present in the ferrous state or ferric state, we can have incompletely filled D level or the D cell or the D orbitals, which will typically define whether our this Fe2 plus or Fe3 plus, both of them can be considered as the corresponding transition element derived ions. So, these are all transition ions or transition element ions which can be derived from iron, which is Fe0. So, in a similar way, we basically give for the definition for F block, and in these two cases we just considered that since the group will start now, because here we follow that the transition elements are following from periodic table after calcium. Similarly, here these are starting from lanthanum and actinium. So, where the position of this lanthanum and the position of the actinium we should know, and based on that we basically consider that following that. So, once the lanthanum we reach, then the following electron configuration or the occupancy in the cell, which is whether D or F, is different, and this occupancy will considered as again some type of transition metals, but this type the occupancy is not D, but it would be occupancy of the F cell. So, occupancy for the F cell will basically give us something where we can have a group of elements or group of metal ions which we will consider as inner transition elements, because after D we just get again not a ultimate cell, but it is a penultimate cell. Below this 3 D level is the inner transition metals or inner transition metal ions. So, initially if we just simply consider a part of the whole periodic table which belongs to the D block elements, and those D block elements are very important to understand. That means, on the left hand side we have till calcium which has the atomic number of 20, and on the right hand side we have the pre-block elements. So, in between we have in the period 3. So, we have period 1, period 2 and period 3. After when we reach period 3, then only the possibility of coming the corresponding D cell is there. So, after calcium we will be having the element, first element will be scandium. So, then we have the scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So, already we have defined this, we are excluding these, that means zinc, cadmium, mercury from this list, because these are group 12 elements and we cannot consider by that particular definition, that means the incompletely filled D cell which cannot be applied to zinc in its ground state or zinc in its typically available or most commonly available oxidation state, which is zinc 2 plus. So, we will just get for period 4, which is scandium to copper, and what are those electronic configuration that will follow, that these are occupying 3D levels. So, these are also 3D elements or 3D block elements starting from scandium to copper. Similarly, if we go the next period, which is period 5, we get yttrium to zirconium, niobium to ultimately to silver and cadmium. And similarly, period 6 will give you something where we have, you see that 57 to 71, these are by definition, these are the F block elements. And after that F block elements, then only we will get the electron occupancy or electron filling to the D level, which is hafnium, then tantalum, then tungsten to ultimately to gold. So, these three we mostly or commonly encountered. So, this particular group, that means from scandium to gold 79, we see that if we just see in the group level also, the group similarity will also be there. So, all these we considered as the triad, because these are not naturally occurring elements for the period 7, only some synthetically prepared elements have been accumulated over there, and day by day we are just filling up all these levels. Already we have filled up all these levels till this 111 atomic number, but these three periods, particularly period 4, period 5 and period 6 are very important to study these things. And we know that one particular, that means the clubbing of all these elements we put together, that means the 3D elements or 3D block elements or D block elements for scandium to copper, we feel that how their properties are changing as we move from scandium to titanium to vanadium to nickel to copper. Similarly, as we move from this particular period 4 to period 5 to period 6, what is changing? We are just changing from 3D to 4D to 5D elements. So, down the group, that means group 4 elements, group 5 elements, group 6 elements and group 7 elements and group 8 elements. So, down the group, how the properties of all these groups can change, because the ultimate electronic configuration will be same, such as that of our nickel, which is group 10 element, and of 3D, and of 4D it will be palladium, and for 5D it will be platinum. So, if we just consider something, that means initially we do not know much, because we are not very much concerned about the corresponding chemistry of the metallic part, because this relation to the metallurgy and the metallic part or the alloy formation. But if we take out those 2 electrons, that means 2 s electrons on the left hand side. So, s electrons will be losing first. So, we are remaining with the d electrons for its cationic form, which is Ni2 plus. So, if we have Ni2 plus from here, similarly if we can have palladium 2 plus or if we can platinum 2 plus, in all these cases we will see that the corresponding configuration in terms of the occupancy in the D level will be 3D some number, then 4D some number, and then 5D some number. Similarly, these properties, that means from iron, ruthenium and osmium, but interesting thing is that as we move down from iron to ruthenium to osmium, and the size of the d cell or size of the d orbitals are increasing enormously, and the corresponding properties and the reactivity patterns are also changing. So, the next thing what we will be seeing that how we can consider that what should be the electronic configuration of say scandium 21 or say platinum 78. We should have some good idea how quickly we can write that it has the ultimate electronic configuration for scandium. Scandium 0 is 4s2 3d1. That means the first electron is entering in the level which is 3d, and that means that we have the unoccupied 3d level. So, scandium by definition falls under that category of transition element. So, titanium will be in the similar way, that means the 4s2 3d2. So, what we are getting starting from group 3 to group 11, we are getting d1, d2, d3, d4, d5, d6, d7, d8 and d9 system. So, another way of classifying or placing all these in the periodic table is important, such that we quickly consider that in a particular oxidation state, we can have electronic configuration which is also known by its positioning in the corresponding group. So, what we see that in the long form of the periodic table, that means the color which will be telling us that the pink color will be telling us that these are the transition metals. So, scandium to corresponding gold. So, this group and the left hand side we have the corresponding S block elements, and the right hand side we have the P block elements in this side, and then the group which is inert also we know. And as we move from here, that means after lanthanum we will be getting the corresponding occupancy like that 10 electrons in this particular group. Similarly, we have 14 electrons in the F level. So, after lanthanum we get the series from here to here, that means cerium to lutetium. These are known as lanthanides. Similarly, after actinium, whatever element, that means the 14 elements will be pushing there due to the occupancy of the corresponding 5F level are known as correspondingly actinides. So, these two groups will be coming over here. Before that, we should finish our discussion in relation to the corresponding transition elements, and mostly we always concern about the particular part which is the first transition series, because we know very much, because these are mostly commonly available on the earth crust, because as minerals and ores the corresponding abundances are more, even they have present in the biological form in the biological system, even in our body, because iron, we all know iron is present in our body also, and a particular process like the process we call is a mineralization process. That mineralization process is responsible for storing iron on the earth crust. Similarly, other process which we can consider in a similar way, that is the biomineralization process, and that biomineralization process can be considered for storing iron in our body also for the synthesis of hemoglobin and myoglobin like things. So, these elements are so important that we should know very much, because they have different interesting properties related to the transition elements. So, the definition is that for pink element that we have partly filled D levels, and for these two groups for lanthanides and actinides we have the partly filled F cells. So, if we just consider that what about the period 4 transition metals. So, we will be just knowing now that what are those metals, because we quickly will see that a particular type of metals, what we will see that we can have these corresponding properties of these metals, particularly how we can store. And just now I am giving some examples, that iron we know, that iron in a metallic form we know, that iron nail we know, iron nail or iron sheet we know. So, use of iron we all know very much. Similarly, if we get something that the corresponding ions Fe2 plus and Fe3 plus, And if I now say that any of them is also present in our blood as hemoglobin and myoglobin. So, this particular thing will concern about the corresponding transition metal ions. These are not metals. So, the corresponding property of these thing is that we have the corresponding property of these, and how this iron will look like. Some of us have some good information about what the iron nail will look like, iron sheet will look like, but what are these particular things will be in solution. So, whether this will be soluble in water medium or any other medium, and how they will also look like. And similarly, some of these elements can also be useful for the alloy formation. So, before going into that particular detail, because iron, what we know that iron is also present from the ore and minerals, because this will all be present on the earth crust and if they are present as some oxide, and in all of our redox classes, then the previous classes we have identified that how we can recover iron, elemental iron or the metallic iron from all these ores. So, this is a typical process which environment does for us, the earth is doing for us, and we are storing that particular one. And when we recover, so recovery process is typically the corresponding metallurgical process. So, this is the corresponding metallurgy we can have, and that giving rise to the iron 0. But how this iron, basically iron will look like? Suppose if you are given with some iron powder, because it has some important property for this iron as a dust particle type of thing. So, how this iron powder will look like? So, only some examples for this period 4 transition metal. The first one is a typical example for scandium. This is the metallic scandium. So, metallic scandium is there, which is the corresponding group 3 element, and if we put that on a petri dish, so the metallic form of scandium will look like of this type. Similarly, the titanium, these are granules. So, if we have the corresponding ore from the earth crust, so ore for the titanium also we know that titanium dioxide, TiO2 is the typical ore for that. So, titanium dioxide is there, and from there we just have to go for the corresponding reduction. So, the mechanism is there that how to get titanium from TiO2. So, in the metallic form if we produce that thing, so in the corresponding granules are forming and the titanium. So, we that particular thing will also give us the properties what we are just now discussed, that it has a luster, it has a strength and all these. So, the corresponding metallic properties for all these things will be there. So, we get that for the corresponding vanadium also. Vanadium we just once we move to vanadium, vanadium will also give us something where the color of these things are changing. So, if I put something, that means how nicely we look all these things, that means from the nature of all these things, particularly the color of all these and the metallic luster of all these things, we can identify it immediately whether it is scandium, this is titanium and that is vanadium. So, these all have different. So, the particular nature of this particular units, that means the corresponding granules, the nature of these granules, these are not typical powder, because some other process we have to go for getting the corresponding powder. Similarly, chromium, you see the chromium also look like a chromium powder. So, this a chromium powder we can have. So, this is a more powdery form, this has less metallic luster type of character. So, it is forming a typical powder type of thing. Then manganese, manganese you all know the most typical corresponding ore is the pyrolusite, which is manganese dioxide, which is plenty in nature. India is also very much rich in having manganese dioxide or pyrolusite. So, the mining process basically gives us the mining for manganese, we take out that particular ore, and the industry, the metallurgical industry will give rise to the corresponding manganese. So, if we consider that in some cases we basically get that particular thing, that where we can have that particular manganese typically in our hand. So, manganese will be for the particular manganese metallic state. So, these metallic state we can use sometime, because most of these are as metal, they can also react nicely with the acids. So, the oxidation process, because we all know now that they can liberate hydrogen from the acid. So, direct reaction of all these can liberate hydrogen, and the metal will go to the corresponding ions, like that iron, when it reacts with hydrochloric acid, iron powder. So, this powder from the petri dish what we can take. So, if we react with hydrochloric acid, the corresponding salt what we will be getting is the ferric chloride, and hydrogen evolution can take place. So, the corresponding iron powder, which can also be identified from the ores like hematite and magnetite. Cobalt is also very much similar to that of our vanadium case. So, it has also typical luster. So, is a typical globules having a shiny appearance. So, shiny appearance on the surface of this will tell you that this is a cobalt thing. Then nickel is also of different nature. That means, when we go for the corresponding crystallization from a molten state, because all these at high temperature we are getting as in the molten state, and when we go down to room temperature, they basically crystallize it out in a typical form. So, the metallic nickel will be separated out from in that particular fashion. Similarly, this is copper. So, copper is also the last species which we will get, because already we are having 4 plus 4 plus 8 plus 9 elements we just reached there. Then we can have the zinc. Zinc we have the 3D10 arrangement, because the zinc granules, zinc powders, and all these are very important to understand the positioning of this particular as a, whether it is a transition element or not, but the zinc will not be a transition element, because in the elemental state or in the metallic state it has the corresponding electronic configuration of 4s2 3d10. So, if we just take out those 2 electrons, so the electrons will go from the 4s level. So, the 4s2 electron will go to give you a 4s0 electronic configuration, leaving behind with 3d10 electronic configuration. So, that 3d10 electronic configuration will give you a filled 3d level. So, zinc will not consider as a transition element. So, already we have discussed how we can jot down these physical properties. So, as inferred by the name, the transition metals are metals and thus conductors of electricity. So, whatever the species what we just now have seen as the corresponding metals, because in some of our next classes we will be discussing about the corresponding formation of the transition metals. So, if we have the corresponding metal which just now we have seen as the Fe0, so it has all metallic property inherent to it, but when we move from there to say Fe2 plus or Fe3 plus, so this is a typical electron transfer process we all know, and this is the oxidation process, but whatever things we will be producing in solution in water, and these will be present in aqueous solution, these two are in aqueous solution. So, these ions in solution, so these are, we can consider them as transition metal ions. So, whatever we have such as this present in blood, if they are present in blood in this particular 2 forms, that means either iron 2 or iron 3 or any other biological system. So, those are we considered as the transition metal ions. So, we should always be very much particular that you have ions. So, these are forming with the corresponding ions, not the corresponding metals. So, if we just consider that these particular metals and thus they have the good conductors of electricity. So, the iron wires and all these things we can have, we know aluminum wires like that of we have iron wires. So, that particular, then we have the good conductor of electricity we are using electrical wires, the copper wires, and they are highly dense. So, they have a high density and high melting points and boiling points also. So, if we consider that corresponding thing, that what we get the corresponding properties is due to the progressive filling of the D cell but the filling of these levels will give you the corresponding metallic character of these. So, the metals when we talk, their properties are due to the corresponding 0 form, that means that iron 0 or nickel 0, and they have the typical metallic bonding. So, we will not consider all these things in this particular class, but we should have some little bit idea about what is called this metallic bonding. So, just now we have seen that in case of 4s element and the 4p elements, we have the ionic bond, typical ionic bond and the typical covalent bond, and in between we can have for 3d elements in the metallic state, they can have metallic bonding. And in the metallic bonding case also, when we will consider the typical bonding for the corresponding metal ions, there also will find some interesting thing for their participation in the corresponding bonding when they participate as the corresponding transition metal ions. But what about in the free form, that means in the 0 form, in the metallic form, they also participate for the corresponding delocalization of the d electrons, and that is why they increase basically their cohesion due to the large number of these electrons, because we know that the capacity of d electrons when it is filling in zinc, when it is filling completely in cadmium, when it is filling completely in mercury, they have 10 electrons altogether. So, as we have discussed, what is the typical indication that we are not getting as this particular one for the mercury, which is typically a different thing, which is the filled d level. So, all these, not only mercury, but starting from zinc, which is 3d filled, so is 4s2 3d10, then cadmium 5s2 4d10, and then mercury 5s2 6d10. So, these all will have lower melting point. So, the melting point is less, boiling point is also less, because they have full d subcells and they do not participate much in delocalization and sharing of d electrons, and they do not have very good dd bonding in relation to increase the corresponding metallic bonding. So, the conduction band they form, but the corresponding dd bonding will not participate much in forming the corresponding character, and as a result the highest one, that means the mercury, will have a very low melting point of minus 38.83 degree centigrade or minus 37.89 degree Fahrenheit, is a liquid at room temperature. So, is basically is failing. So, from that particular one, that metallic property is not there, but it has other properties, though it is in liquid. So, other metallic property will be there, but it is not a transition metallic property we just expect from there. So, the first 3D series we just now take out partly, because we will be talking about their properties, because what about these d block series. So, these d block series will be there if we just simply talk in terms of the corresponding appearance of the corresponding oxidation states, because just now we have seen from scandium to zinc how they look like. Now, if we take out the corresponding reactivity pattern of these, so the one of the chemical reactivity, physical reactivity, we all know that how they form alloy, what is their metallic luster, whether they are conductor, all these, but what about their corresponding ionization? So, ionization is their corresponding reactivity pattern with the acid, whether your acid is oxidizing or not. That means the reaction with hydrochloric acid, the reaction with oxidizing acids like nitric acid or sulfuric acid. So, that will give rise immediately whether we are able to get the corresponding salt formation, that we have seen that zinc, the metallic zinc or the zinc rod, in our previous redox chemistry classes we have seen that zinc rod can lead to something where the evolution of hydrogen can take place, and we can give rise to the corresponding metallic salt starting from zinc oxide or the zinc itself. So, this particular thing that now we can just separate it out quickly from group 3 to group 11, including the group 12, because we reach ultimately the 3d10. So, the atomic number, the elements and the configurations. So, configurations we can have some good idea. So, separating out of these scandium to zinc, and what about this particular possibility is also there. That means once we know that the zinc, then copper, then nickel, which is a 3d10 element, then we have the 4d, then 5d. So, zinc, copper and then nickel, when we reach down to nickel, then downwards we have the palladium and we have the platinum. Similarly, when we iron is 3d6 4s2. So, if we go what we are just now seeing, that if we know the configuration, that means the positioning in the group, the corresponding atomic number also. So, this we can find out. It is not that you have to memorize all these things, but you should know that is atomic number once it is 26 by filling up the electrons from left to right from 21 to 30, where your position of the iron and its electronic configuration. So, if it is 3d6 4s2, so this iron which is 3d6 and 4s2. So, it is in the 0 state. So, when it is losing 2 electron, it is losing 3 electrons. So, straight away we will not consider the electron occupancy in this particular level. So, we will straight away will write that is a 3d6 ion. So, ferrous is a 3d6 ion, and this particular case what we will see that we have the most two common oxidation states. So, for iron here we will just simply write as we know that also for our blood in our body, that either you can have iron 2 plus or iron 3 plus or something which is in between, or something related to its corresponding reduced form of the ferric. So, this Fe3Ps and this, so these are most common oxidation states, which is very important, that how facile they are. That means, the formation of these by simply reacting with say dilute hydrochloric acid, cold and dilute hydrochloric acid which is aqueous. So, the reactivity of the iron powder, how we have seen that what is the iron powder. So, reactivity of these iron powder will just lead to the evolution of hydrogen. So, hydrogen evolution can take place, and the corresponding ions will remain as the chlorides are there. So, we will having the corresponding thing as the ferrous chloride, and if it is oxidizing, because these the redox potential, the redox couple between these two are less, the E0 value for these two are also less, which is 0.77 volt. So, if oxygen is there, oxygen is much more oxidizing. So, it is in air. So, if we handle everything in aqueous solution, so already the water present for this aqueous solution or the preparation of this hydrochloric acid. So, O2 is there. So, this particular aqueous solution, so O2 is the oxidizing one. So, O2 is oxidizing agent. So, that will immediately oxidize this to Fe3 plus. So, what about this particular electronic configuration? So, electron configuration for Fe3 we have to take out one electron from this 3d6. So, it will not be 3d6, it will be 3d5. So, for these two, that means we have 3d6 ion and 3d5 ion, which are most common oxidation states for 3d level. So, since we are talking about 3d. So, if we just consider the periodic table, so in the periodic table we have iron, ruthenium and osmium. So, which is 3d, 4d and 5d, and these are giving rise to some electronic configuration. So, if we consider that all of them are giving, that means the trivalent state for iron, trivalent state for ruthenium and trivalent state for osmium. So, this is the electronic configuration which is 3d5 for iron. So, iron 3 plus will be 3d5. So, without knowing much or without bothering much about what would be for ruthenium. So, ruthenium will be ruthenium 3 plus, this is iron 3 plus. So, iron 3 plus will be 3d5. So, ruthenium 3 plus will also be 4d5. Similarly, osmium can go for osmium 3 plus, which will be 5d 5. So, this is the advantage of knowing the periodicity of the elements, placing them in the periodic table, and how quickly we can understand when we talk about the chemistry of these, because sometimes we can handle all these in solution. Having some test tubes, we can have some test tubes, test tube 1, test tube 2 and test tube 3. In one case we have ferric ion in solution, in another case ruthenium in the trivalent state, in other case the osmium in the trivalent state. So, the generalization of all these things are very important, and we know that most of these cases we are removing the electrons from the d level. That means, this oxidation, the first 1 electron loss, the first 1 electron loss for getting ferric ion from ferrous ion is the removal of the electron from the d level. So, this is much more facile, but if we can have some arrangement and if we can have some stronger oxidizing agent, so then we can find it out whether we will be able to take out the electrons from its corresponding positioning. That means, whether we can go beyond, that means whether we can take out more number of electrons from these. That means, we can take out one more electron from this level, giving 3d4 or 3d3. So, those oxidation states we can get, and those oxidation states will be termed as unusual oxidation states or uncommon one. So, uncommon oxidation states we can have, that means beyond this. So, 2 and 3 can be there. So, we can have 4 plus, we can have 5 plus, or we can have 6 plus. But altogether what we can have? Altogether we can have 8 number of electrons, 2 in S level and 6 in D level. So, if we remove all these electrons from S level or S cell and D level or D cell, we will be getting something which is 8 plus. So, whether we will be getting that particular one is important to discuss, whether it is possible for iron and whether it is possible for all other elements. So, what we see that getting all these oxidation states, that means plus 2, plus 3, plus 4, plus 5 and plus 6. So, these elements, these transition elements therefore occur in variable oxidation states. So, they basically occur in variable oxidation states. So, one or the other, that means as we move, that means the corresponding filling off of the D level from scandium to iron, we are filling off stepwise one after another, 1 electron, 2 electron, 3 electron, 4 electron, 5 electron and 6 electron. Similarly, when we are talking in terms of the removal of electrons from that particular D level or D cell is the corresponding oxidation reaction. So, solution chemistry for all these metal ions will be mostly dominated by the presence of the corresponding oxidation states, and we should have some good knowledge about the presence of all these oxidation states in our hand. So, we get this as the 3D elements or D block series in the third level. Similarly, we get the next one, which is the second D block series, which is from Y to CD or yttrium to cadmium, and again like that of our electronic configuration or the positioning of all these things, we see that in this particular case also the progressive filling of the D cell is important, and we have in some cases we have the mostly from here, that means D1 to D9, because this we just move for that. If we move this electron to the S level, which will be 5s2 and which will be 4d9, we get the progressive filling of the D cell. So, we will get these, and since this particular one we are talking about, so this particular one, since the size is increasing, instead of writing as D6s2 electronic configuration, we can move, because these are very close by energy wise, these levels are very close by the D level and the S level. So, we can move this particular electron to this particular cell. So, that is their configuration is now is 4d7 5s1. So, that basically tells us something that whether we can have that removal of single one electron from the s level. So, removal of that particular one electron will giving rise to a state where you can have ruthenium in 1 plus state. So, in a particular condition or in a situation that we will find afterward, that one particular type of compound we call as the organometallic compounds, where we can have some interaction of this metallic state in the 0. That means, the powders can react with some of the species like that of our metallic state, which can interact with that particular thing, that means simple carbon monoxide. So, 3D congener of this palladium is nickel. We all know that nickel can interact with carbon monoxide, giving rise to tetracarbonyl nickel 0. So, nickel will be 0. In that particular case is the organometallic compound, and that organometallic compound will have a electronic configuration. We just consider that electronic configuration in terms of nickel 0. Similarly, if we something that palladium 0 in different organic chemistry reactions, the palladium 0, the metallic state of palladium is important, and the corresponding electronic configuration, if we push all these electrons to the d level, because this has a extra stability, the stabilization we all know that the half filled cell, that is why this particular cell we are writing instead of 5s2 4d4 we write as 4d5 5s1. So, one electron we move from s level to d level. So, it has some extra stability, that means the half filled cell and the full filled cell. So, the palladium in that particular case, that this the palladium in the 0 state will have a full filled state, and that full filled d level will have a 4d10 electronic configuration and is stable. Similarly, the other one, that means the 5d block, and the 5d block will get the corresponding one from that lutetium to lanthanum. Sorry, this lanthanum is 71, this not lutetium is lanthanum La, it would be La to this gold. So, there we are also having just simply the same type of electronic configuration and same number of electron in the d level and the s level, but thing is that now we can have the corresponding occupancy of these levels and is changing from one particular level to the other. We are talking something related to 3D level, 4D level and 5D level. So, the corresponding occupancy of the corresponding period, that means the period which we are talking about for 3D, 4D and 5D. So, in this particular case these are the 5D element. So, the cationic state, just now what we have discussed, that osmium like iron. So, after iron we have ruthenium and then we have osmium. So, osmium is the congener of the iron group. So, in that particular case we should not forget the group number. Similar fashion we should know the atomic number also nicely, and the osmium is in +2 oxidation state like that of our iron will be 5d6 electronic configuration. So, all these things and the particular type of bonding in all these cases what we see is related to the corresponding occupancy of all these d levels, and we will just be able to consider the different thing, that means the 3D, 4D and 5D elements. So, these 3D, 4D and 5D elements. So, we have if we just consider these 3D, 4D and 5D elements in its elemental state, that means M is in 0 state. So, physical properties are also changing when we talk about the bond strength. So, bond strength will also be changing, and this particular bond strength trend is there. So, as we go for bigger and bigger d level or d cell, the bond strength trend will be changing, and which is a different one, which is a reverse one for this. So, this trend is reverse to that normally we found for main group elements, that means the S block and P block elements. So, what we find for main group elements is different for these transition elements. So, we find that once we get that means, if we consider that, what about tungsten then, which is in the chromium group. So, we have chromium, molybdenum and tungsten. So, chromium, molybdenum and tungsten we have, and in this particular case chromium, we know that this has 6 unpaired electrons. Similarly, molybdenum will also have 6 unpaired electron. So, we have 5 D4 and 6 S2. So, all these 6 electrons, if we consider the corresponding property as its 0 state, that means tungsten in the metallic state. So, the tungsten in the metallic state have the 6 electron, and these 6 unpaired electron, they participate strongly in metallic bonding. So, we have large number of electrons which are not possible to get for S level or the P level elements. So, large number of electrons are available for these. So, as a result, they can have also very high electronegativity. So, tungsten will have therefore have very high electronegativity. And this particular information is also important from our early school days. We know that they can be utilized. So, they have a very high melting point and high boiling point. So, tungsten, the metallic tungsten will have very high melting and high boiling point, and as a result they can be utilized for making the bulb filament. So, the bulb filaments for incandescent lamps, we use tungsten as the corresponding material for the making of these bulb filaments. So, we can have these, that means we just corresponding unpaired electrons. So, we basically change the corresponding melting point. So, we just can see also what about the corresponding melting point trends also. So, as we move from scandium to titanium to ultimately to zinc, so we find that the typical melting point in degrees centigrade will also be changing, and which are above 100. So, mostly it is above 1000. So, not sorry, above 1000. So, above 1000 degrees centigrade, and in some cases they can go up to 3000 degrees centigrade. So, one value is 1539 degrees centigrade for scandium. So, it is increasing for titanium, it is increasing for vanadium as well as chromium, but in case of zinc it is less, since those number of electrons which are there, but is in the filled cell, it is not available for that kind of metallic bonding. So, minimum will be finding over here where the levels are filled. So, the melting point minima will be finding over here, and melting point maxima will be here for the transition metal ions. So, thus we see that number of electrons in the elemental state, we will not forget that all are in the elemental state, that means the scandium as the metallic scandium, titanium as the metallic scandium, they have the high melting point, high boiling point, and some of these uses related to the metallic state. So, the next day we will be just considering how we get for the corresponding electron transfer reaction for the oxidation, that means the availability of the different oxidation states. Okay. Thank you very much.